So I said the valence shell electron pair repulsion theory is all about, and I kind of did an atom here, the shape around an atom as it bonds to other things, and I kind of did like this. And the things that scatter, the things that repulse, are going to be what? The sigma bonds and the lone pair electrons. I'll just put dot dot for lone pair electrons. So those two things are going to repulse from each other. We kind of say that those things create, I like the word electron domains, electron pair domains. This actually says that things that are going to kind of repulse from each other to create shape around an atom is going to be lone pair electrons, single bonds, and this kind of says if you have a double bond, that's going to count as one group. Why? Because with a double bond, you have one sigma bond and you have one pi bond. Remember, the pi's do not give shape, but the sigma bonds do. We're kind of similar. If you have a triple bond, that actually just represents one group. Why? Well, if you have a triple bond, how many sigma bonds do you have that create shape? Just one sigma bond, and you actually have two pi bonds. Okay, so kind of keep that in mind. So these are the things that are going to repulse in the valence shell electron pair repulsion theory and give shape around an atom. This is a handy little chart you're going to want to, I guess, kind of commit to memory. So if you have two things that are repulsing, and I'll go ahead and talk about those electron domains as either being where sigma bonds are extending from that atom, or there's a pair of lone pair electrons that create shape, that actually, you'll have two things. The shape, if they repulse as far apart as possible, is going to be linear, okay, for that atom, okay, and the bond angle is going to be 180. Now this, don't worry about too much, although I will be referring to it. If this is the case, then what that atom has undergone is taken one of its s and one of its p and hybridized those atomic orbitals and spit them out into two equal hybridized orbitals called sp hybridized orbitals. Is that not cool or what? So you're going to want to kind of know that. We'll kind of wrestle with this in lab this week. So if you have three things extending from that atom, now those things can only be sigma bonds, this is the repulsion part of it, sigma bonds or lone pair electrons, a total of three, then you basically have a shape, is repulsing as far apart, it lies in a plane, and it's three, it's trigonal, so trigonal planar. And I've got some images here to kind of show you what trigonal planar looks like. That atom must have taken one of its s and two of its p's and hybridized them and spit back out three equal hybridized orbitals. The bond angle for a trigonal planar shape around an atom is 120. One more row, okay? If you have four things, now in the case of valence shell electron pair repulsion theory, those two things extending from that atom would be sigma bonds or lone pair electrons. If you have four of those things, they are going to spread apart and create a shape we call tetrahedral. The angle between those bonds will be 109.5, okay? And the type of hybridization that atom must have undergone to create that situation was to take one of its s and three of its p's, okay, and squish them all together. I like the word hybridize. It's kind of like genetics hybridization. It takes them and it takes these four atomic orbitals, it combines them and spits back out four equal orbitals. Is that not cool or what? Now one more thing before I leave. You are going to have to know these three different types of atomic orbital hybridizations. Now, it's something called, you know how we say mass is conserved, energy is conserved? Well, here we say orbitals are conserved. Orbitals are conserved. And what I mean to say is, for instance, if you take this orbital hybridization, it took one of its s and one of its p, so it spit out two hybridized orbitals. Down here, it took one of its s and two of its p's and spit back three. You see what I mean? That little superscript, see, it says how many of that type of atomic orbital it took into its hybridization process. So sp3 is 1, 2, 3, 4. Okay, so it's conservation of orbitals. Now I've got some pictures coming up to see what you think. This is probably the most complicated of the pictures I'm going to show you. So the way it works is we've got columns again. I'm kind of hiding one column for now on purpose. Okay, I'll put a question mark there. So in this first case, we have a possibility for having 2 electron groups. Now that first column, if you want to write, these are your sigma bonds, and these are your lone pair electrons. Okay, that's what we're going to count. Or literally, if we're looking at a Lewis structure, we're going to count sigma bonds and lone pair electrons to understand what sort of geometry we have. I just want you to worry about electron pair geometry or structural geometry. Okay, in that case, I talked about a bond angle of 180, and here, or somewhere if you want to, I call that SP, orbital hybridization. Examples, or an example of that is carbon dioxide. So can you see on this Lewis structure, if we're just talking about the geometry around the carbon atom, we have a double bond here, which is just 1 sigma 1 pi. We have a double bond over here, 1 sigma 1 pi. So can you see where I have 2 check marks? That's kind of what I mean by that. Okay, take it up a notch. And what if instead of 2, what if we have 3 electron groups? Again, I said those must be sigma bonds or lone pair electrons. An example here is picking on this carbon atom. So geometries are all, or structural geometries for this course are all just around an atom. So you kind of have to put blinders on to kind of the stuff that's happening with other atoms. If we count sigma bonds, I got 1, 2, 3 sigma bonds. Remember, a double bond is 1 sigma 1 pi. So if that's the case, okay, we call that what? sp2 orbital hybridization. Now it doesn't look like it. It kind of looks like there's a right angle here, right? Okay, looks like a 90-degree angle here. But this structure kind of shows that actually this bond angle is 120. Okay, it's what we call trigonal planar. And then the last one I need you to, I have another example of a trigonal planar. Now the first example of a trigonal planar, we had sigma bonds all around it. This one actually, we have sigma bond, sigma bond. I'm just talking about the sulfur atom. I'm not talking about the oxygens. Sigma bond, and here we have a lone pair electron. That gives us our third electron domain. Notice if you have 3, then you're talking about sp2, again, orbital hybridization. It's trigonal planar. Your bond angle is 120. So can you kind of see this 120 here? Now, not shown here is kind of an electron, this electron pair right here kind of extend out here to literally create a repulsive force. That's why they count in the shape. This last set, I've actually got 3 examples here. These are all where you have 4 electron groups. Again, those could be sigma bonds or lone pair electrons. In each case, I'm going to put a star here. We're always kind of talking about the central atom. Central atom, central atom. We're just talking about the structural geometry around the atom in the middle. So if we look at methane first, let's count. I get 1, 2, 3, 4. Yep. Okay. Now, if you have 4 sigma and lone pair electrons extending from an atom, that atom must have taken its atomic orbitals, sp3, and hybridized them to spit out 4 equal hybridized orbitals. So the bond angle then is going to be approximately 109.5. And so this angle right here is 109.5 degrees. Ammonia, so here we have 3 sigma and 1 lone pair electron. 3 plus 1 is 4. That's your 4 over here. And anytime you see 4 sigma bonds, lone pair electrons, you better be thinking sp3 orbital hybridization. Water, H2O, it looks pretty simple, doesn't it? Well, let's count sigma bonds, sigma, sigma, And then each lone pair electrons counts as an electron domain that gives shape to that oxygen atom. So I'm liking 2 sigma plus 2 lone pair electrons. I'm getting 4 here. Okay, so that's why it made it sp3 orbital hybridized, and the shape around that oxygen atom, including these invisible invisible lone pair electrons, the shape is tetrahedral, and this bond angle is approximately 109.5. We'll be talking more about how that approximation kind of works. Now this last one, if you have it on the slide and you feel like you want to, you can go ahead and cross these out, because we aren't not going to step back and look at what the overall shape of the molecule is. I just think that's too confusing. I want to focus on an atom. All right, so here we go again. Do you see the electron pair repulsion theory? You see the repulsion part. So this is your atom. These are your electron domains. They can extend as either lone pair electrons or sigma bonds. In this case of BeCl2, the Be is in the middle, okay, singly bonded to chlorines. Okay, so that's sp orbital hybridization, linear. This is sp2 orbital hybridization. Here we have this is Bf3, so we have a boron, sigma bond, sigma bond, sigma bond. Okay, 3 things, no lone pair electrons. This is sp2 orbital hybridization. We call this trigonal planar. Can you see where it lies in a plane? So that's kind of nice, the bond angle 120. The last one I'm holding you responsible for is this one, where you have 4 things, 4 pairs, sp3 orbital hybridization. When they scatter, they make this shape like this, we call tetrahedral, and the bond angle is about 109.5. See how I think the pictures are real important. So you're going to have to know, I kind of like, and you're going to have to be able to interpret from a final Lewis structure what the shape around an atom is. So these are balloons, and kind of in the center where the balloons are joined, you can kind of think of the atom that's extending either sigma bonds or lone pair electrons, sigma bonds to connect with another atom, or just lone pair electrons to give geometry around that atom. So here we have an atom here, and this is neat because you kind of see that balloons naturally want to kind of get their own much space as possible. So that's the repulsion part, I think, is really cool. Here we have sp orbital hybridization, linear shape. This is sp2 trigonal planar, sp3 tetrahedral. Now, there's 2 other figures on this slide, and actually the next couple of slides too. These are additional atomic orbital hybridizations that an atom can undergo. Again, here's your atom here, and here's your atom here. You can see there's more electron pair domains extending from that atom. In this case, actually, I'll do it this way. We have 2, 3, 4 things extending. Here we have 5 things extending. Here we have 6 things, those things being sigma bonds or lone pair electrons extending. So this actually is trigonal bipyramidal, and it is an sp3, and then it's exciting, it takes one of its d orbitals. Is that not cool? Okay, again, conservation of atomic orbitals. If you add the superscripts 1 plus 3 plus 1, you get 5. This last one over here is, guess what, sp3d2. Conservation of orbitals, you add 1 plus 3 plus 2, and you get 6. So this was how these things scatter. It's pretty cool. I'll have some more pictures to kind of show you that. So I feel a little bit like I'm repeating myself here. Again, kind of think of the atom in the center, okay, and it's extending either lone pair electrons to create shape around that atom or a sigma bond. Okay, there we go, and there we go. So hopefully, I like this one. Can you see the trigonal planar? This is linear. That's sp2, trigonal planar linear is sp. Goodness, trigonal planar sp2, tetrahedral sp3. And then here are our sp3d and sp3d2 again. They're kind of cool, aren't they? I think this is easier to see. They kind of have this plane kind of situation in the middle. That gives it its trigonal part, and it's bipyramidal because it extends up and down. That is so cool. And then this is the octahedral, where it also has kind of 4 electron domains extending in a plane, and then it goes north and south like that. Again, you know, I feel like I'm kind of repeating myself. Okay, this clearly says, it kind of goes back to the first slide in this part. These are all the geometries. These are structural geometries. Structural geometries. And I'm pretty sure that's kind of universal in chemistry. Structural geometries would be just a singular atom. Atom shape, or shape around the atom. Yeah. And again, you only need to know these first 3. The SP, SP2, and SP3. So let's take a look at what you might run into on your test. I'm going to leave this for our next section.